Hi chemistry students. In this video you will learn how molecular shape is important with regard to disease and drugs. You will learn whisper theory. You will learn how to draw molecular shape. You will learn polarity in terms of individual bonds and an entire molecule. And at the end you will learn how to deduce and draw a dipole moment for an entire molecule. Before we start learning three-dimensional shape of molecule, let's look at the way we were looking at the molecules in the past. So far, we have been looking the molecules with the help of Lewis dot diagram. And with Lewis dot diagram, we represent molecules and draw them as flat molecules. For example, we represent ammonia and methane as we have in this image, like a two-dimensional flat molecules. These Lewis dot diagrams only show how atoms are connected in a molecule and how valence electrons are arranged in a molecule. However, neither methane nor ammonia is actually a flat two-dimensional molecules, but both of them have much interesting three-dimensional shapes. So in this video, you will learn how to convert a two-dimensional Lewis dot structure to a three-dimensional shape of a molecule. Molecular shape is important in determining how molecules interact and react with each other. One important area where shapes of molecules is important is pharmaceutical industry. How drug molecules work in a body is dependent on shapes of drug molecules. Understanding how molecules have their particular shapes is therefore very important for chemists, especially when we want to design a new drug to fight a particular disease. In this image, I have a drug, thalidomide. This drug was used to prescribe to relieve morning sickness in pregnant women. This drug caused a worldwide tragedy. The drug was prescribed to release pregnancy nausea, but later it was found that thalidomide caused irreversible damages to the fetus, and thousands of children were born with severe congenital malformations. Many of them did not survive more than a few days after they were born. The reason came from the shape of the thalidomide. Thalidomide exists in two mirror image forms. It is a racemic mixture of R enantiomer and S enantiomer. The R enantiomer relieves morning sickness, whereas S enantiomer causes severe birth defects. And under biological conditions, these isomers are interconvertible, so separating these before use is ineffective. Therefore, it is really important to learn molecular shape when determining how molecules interact with other molecules, like with protein molecules in a human body. Let's see how to predict the shape of a molecule. Whisper theory or valence shell electron pair repulsion theory is a model that is most commonly used to explain three-dimensional shape around a central atom. Whisper theory is based on simple concept that the valence electron. Here the straight line between carbon and hydrogen indicate the covalent bond between carbon and hydrogen, and you know that each covalent bond have two electrons. So atoms are surrounded by clouds of negatively charged electrons. And when you have many atoms in a molecule, like in this example, these negatively charged electron clouds repel each other. In two-dimensional Lewis dot structure, these electron clouds right now are at 90 degrees apart, but if you let them go, they will take the shape where the bond angle is as far as possible and the repulsion is as minimum as possible. So whenever we have four bonds around a central atom, like in this case, this molecule will automatically adopt a geometry which is the tetrahedral geometry, where atoms are as far as possible. And the bond angle is 109.5. We will see this in detail in next few slides. To predict the shape of a molecule, okay, to predict the shape of a covalent molecule, we have to follow following steps. Step number one is draw a dot diagram for the molecule. Step number 2 is count the number of electron groups around the central atom. Include lone pairs and count each multiple bond as a single electron group. And this electron group is actually called the steric number for the central atom. Using the steric number from step number 2, decide the best arrangement for the electron groups, including lone pair around the central atom. Step number 4 is pretend the lone pairs are invisible and describe the resulting shape of the molecule. We will be using this table to decide the geometry, electron group geometry, and the shape of the molecule. With 4 electron group or steric number 4, the electron group geometry will be tetrahedral and the bond angle will be 109.5. If all the electron groups are the bonding groups and there is no lone pair, then the molecular shape will also be tetrahedral. The second scenario with 4 electron groups or 4 steric number is that we have 3 bonding groups and 1 lone pair. So electron group geometry will still be tetrahedral, but the molecular shape will be pyramidal because we are ignoring this lone pair. Okay, so we count all the electrons when we are determining the electron group geometry, but we treat lone pairs as invisible when naming the molecular shape. So here I have ammonia with 3 bonding groups, 3 bonds with nitrogen, hydrogen, nitrogen, hydrogen, and nitrogen, hydrogen, and 1 lone pair. So we will ignore this lone pair and this bottom part look like pyramidal shape. Now for the bond angle, this lone pair is more negative and will have more repulsion as compared to the electrons that are in the bonding groups. So when this lone pair have more repulsion, there will be a squeeze play and actual hydrogen, nitrogen, hydrogen bond angle will be less than 109.5. A useful rule is that each lone pair from second period element will compress the remaining bond angles around that atom by 2 degrees. But in general, you can just simply say that the bond angle will be less than 109. With 4 electron group or steric number 4, if we have 2 bonding groups and 2 lone pairs, electron group geometry will still be tetrahedral based on the 4 steric number, but the shape will be bent when we ignore these 2 lone pairs. If the steric number is 3 for 3 electron groups, electron group arrangement will be trigonal planar. And in this trigonal planar, if all the groups are the bonding groups and there is no lone pair, then the shape will also be trigonal planar. But if we have 1 lone pair, then when we are giving the shape, we are going to ignore the lone pair and the shape is going to be bent. The bond angle for trigonal planar is 120 degree. And if there is a lone pair, then due to the squeeze play, this lone pair is more negative than the bonding electrons. The bond angle will be less than 120. For 2 electron groups or steric number 2, the electron group geometry will be linear, and in this we will have 2 bonding groups and no lone pair, and the shape will be linear. Let's see how to count the number of electron groups around central atom. We have some rules to count the electron groups around central atom. Here I highlighted the word central atom because I want you to remember that when we count the electron group, we only count around central atom. Central atom can be more than one. Okay, how will you identify central atoms? So a quick tip is the central atom will be connected with 2 or more atoms. And besides central atom, we have terminal atoms. And terminal atoms will be connected with only 1 atom. So hydrogen is connected with only 1 carbon. So this is terminal. Oxygen is connected with carbon only. So it is terminal. This hydrogen is terminal as well. When we come in this example, this hydrogen is connected with only 1 carbon. So it is terminal. This is terminal. This hydrogen is terminal. This hydrogen is terminal. this oxygen is terminal connected with only one oxygen. This oxygen is terminal connected with only one oxygen. For central, it has to be connected with two or more. So this carbon is actually connected with three atoms. So this is going to be the central carbon. Then we come to this example. This carbon is connected with two atoms, one carbon here, sorry, one hydrogen here, and one carbon here. So this is connected with two. So does this carbon connected with two atoms. So in this molecule, we have two central atoms. Here, oxygen is connected with two atoms, so it is central. Um, in this, we have this oxygen connected with two atoms, so this is central. So the first thing is you have to find where you have your central. Once you know you have your central, you will be counting lone pairs as one electron group. You will be counting single bonds as one electron group, and you will be counting each multiple bond as one electron group. So let's do it. So for this central atom, we don't have any lone pair in the central atom, right? So we will go for the single bonds. So we have one single bond here, so that's my one electron group. This is my second electron group. And then this multiple bond will be counted as one electron group. So this will be my third electron group. So altogether for this carbon, we have three electron group. So number of electron groups are also called steric number. So steric number for this molecule is 3, or the number of electron groups for this molecule is 3. Now we come to this example. So this carbon um, does not have any lone pair, so we will go for the single bond. So it has one single bond here, and then we have a multiple bond here. So all these multiple bonds will be counted as one steric number. So altogether for this carbon, we have steric number 2. And for this carbon as well, we have one electron group here and one electron group. These multiple bonds will be counted as one electron group. So for this carbon as well, the steric number is 2. When we come here for water, let's count the lone pairs. So we have two lone pairs, and each lone pair is one electron group. So we have one electron group here, two electron group here, and then you will be counting single bonds as one electron group. So this is your third electron group, and that's your four electron group. So for oxygen in water, electron group is 4. Okay. Now in ozone, so the first thing for oxygen, we will count the lone pair as one electron group. So we have one electron group, then the single bonds. So we have two electron groups, and then the multiple bond is, this is my third electron group. So steric number for ozone is going to be 3 electron group. Let's do the next step, which is from the steric number, now you have to predict the electron group arrangement and then the shape of the molecule. So steric number for formaldehyde, when we did the counting, we have 1, 2, and 3. So steric number for formaldehyde was 3. We are here in this area. So with 3 steric number, the electron group geometry is going to be trigonal planar. And we draw trigonal planar like this. All these bonds will be on the plane. Okay, so that's how we draw trigonal planar. We have carbon in the middle. We have oxygen here. You don't have to draw multiple bonds when you are giving the shape, so you just ignore that part. This is your shape, and we have two hydrogens and one oxygen. And this is trigonal planar. You will be writing the name is trigonal planar. And the bond angle going to be 120 degree. Next example, we have acetylene. For acetylene, the steric number is 2. With 2 steric number, electron group geometry is linear. Okay, so we are going to draw this. So we have the first carbon. We are going to draw this first carbon like this. This part is linear. And then the second carbon is also 2 steric number, so that part as well is linear, and the shape is going to be linear as well. Next example, we have water molecule. In water, we have one lone pair here, second lone pair here. So these are 2 steric number, third and fourth. So steric number for water is 4. And with 4 steric number, electron group geometry is going to be tetrahedral. So we are going to draw tetrahedral like this. Okay, we show that 2 bonds are on the plane, 1 bond is going behind, and 1 bond is coming out of the plane. Okay, and then you can draw oxygen here, then you have your lone pairs, and you have your hydrogen here. Okay, so this is tetrahedral electron group geometry. Bond angle, normal bond angle is 109.5, but when we have lone pair, then due to the squeeze plate, the bond angle is going to be less than 109.5. And what will be the shape for this molecule? You are going to ignore the lone pairs from here, and you will be focusing on this area, and this area, the shape looks like bent, and you can get this from here that you have 4 steric number, your electron group geometry is tetrahedral, there are 2 bonding groups. Bonding groups are these between oxygen and hydrogen, and there are 2 lone pairs. You have these 2 lone pairs here. The shape is going to be bent. For ozone, we have lone pair will be counted as 1 steric number, single bond is 1 steric number. So with 3 steric number, we are going to have trigonal planar electron group geometry, and we are going to draw trigonal planar like this. We have oxygen here, we have 2 bonding oxygens, we have 1 lone pair, right? Its geometry, when we are writing the name for the geometry, is going to be trigonal planar, and the bond angle, regular bond angle for trigonal planar is 120, but when we have a lone pair due to a squeeze plate, the bond angle is going to be less than 120. Shape, when you are giving the shape of the molecule, you are going to ignore this part, and this bottom part, the shape is bent. Let's see how to represent molecular geometries on paper. It is easy to represent linear and trigonal planar on a paper, but little bit tricky to draw a tetrahedral shape. So for tetrahedral, so this image shows the tetrahedral, and in this tetrahedral, these 3 atoms are in the same plane. So we draw these 3 as straight lines. Okay, so you have these 3 bonds are on the plane of the paper. Then, since this is a 3-dimensional, there is 1 atom or 1 bond that is coming out of the plane. So the bond that is coming out of the plane, we make that as a wedge or a dark solid line. And then there's a bond that is going behind the plane, and we have that bond like hashed lines. And you can also draw it like this, that 2 straight bonds are on the plane of the paper, 1 hashed bond is going behind or into the paper, and 1 is coming out of the paper. Okay, let's see the example of a molecule where we have 4 bonds around a central atom. So like the example of methane, right? So when we have 4 bonds around a central atom and we draw that with the help of Lewis dot structure, the maximum angle that we get is 90 degree. And there is force of repulsion between the bonding electrons, and all those bonds are pushing each other far. When we let them go, and they automatically adjust themselves to get the best position where the angles are as far as possible, this is the shape we get for the molecule with 4 bonds around a central atom, and this shape is called tetrahedral shape. where the bond angle is 109.5 degree. So in this tetrahedral, two bonds are on the plane of the paper, or three atoms, like this atom, and the central atom. So those three bonds are on the plane of the paper. One bond, this is going behind the plane, and this one bond is coming out of the plane. So when we draw this tetrahedral on a paper, these two bonds, those are on the plane, we draw them as straight solid lines, and the bond that is going behind the paper, we draw this bond as a hashed broken line, and the bond that is coming out of the plane is the bond that is the solid wedge bond. Okay, so remember that this is a three-dimensional shape. We have two bonds on the plane, one is coming out of the plane and one is going behind the plane. So with four steric number, the electron group geometry will always be the tetrahedral. So this is the tetrahedral with four steric number, 1, 2, 3, 4. Out of these four steric number, this time one electron group is actually in the form of lone pair. So when we have a lone pair, the geometry will still be tetrahedral, but when we are giving the shape of the molecule, we will simply hide this lone pair, and these bonding electron or bonding groups will give you the shape of the molecule. So you can see that when we hide this lone pair, the bottom part, or the bottom bonding electrons are the trigonal pyramidal. So the shape will come out as trigonal pyramidal. And if you have two lone pairs, right? So if, for instance, you have one lone pair here and one lone pair here. So when you have two lone pairs and you are hiding both of these lone pairs, you will be looking at just the bottom part, and this bottom part is bent. Okay, so with two lone pairs out of tetrahedral, you will get the bent shape. With one lone pair out of tetrahedral, you will get trigonal pyramidal. With three steric number, or three electron groups around a central atom, this is the best possible arrangement that the molecule will get. This is called trigonal planar. In this, the bond angle is 120 with the minimum repulsion as possible. And in this molecule, or in this shape, all these three bonds are on the plane of the paper. There isn't anything coming out of the plane or going behind the plane. Okay, and from here, if you have one lone pair, like this is, if this is a lone pair and these two are the bonding, you will be hiding this, and the shape of the molecule will come out from this part, which is the bent shape when you hide this top part. Now with two electron groups, or two steric number, the electron group geometry and the shape of the molecule is going to be linear with 180-degree bond angle. Let's do some practice from this worksheet. In order to find the shape of a molecule, these are the steps. Like, first step is you need the Lewis dot structure. For Lewis dot structure, first you need to find the valence electrons. You will be using a periodic table to get help to determine the number of valence electron. So for oxygen, valence electrons are 6. For hydrogen, we have 1 for each, and we have 2 hydrogens. So total valence electrons are going to be 8 electrons here. For ammonia, we have ammonia from group 5, so 5 valence electron. Hydrogen is from group 1A, 1 valence electron, and we have 3 hydrogens. So again, for this, the total number of valence electron going to be 8. For methane, we have carbon from group 4A, so 4 valence electron. We have hydrogen from group 1A, 1 valence electron times 4. We have 8 electrons here. For next example, we have carbon from group 4A, but we have 2 carbons. We have hydrogen from group 1, but we have 4 hydrogens. So 12 electrons altogether. Here we have 1 for hydrogen, 4 for carbon, and 5 for nitrogen. So total we have 10 electrons, and in this last example we have 8 total electrons from carbon and 2 electrons from hydrogen, so we have 10 electrons. Next step to find the Lewis dot structure is you have to pick the central atom. We have few rules for the central atom. One is hydrogen can never be the central atom, right? Second, when you have atoms in a molecule and you have to pick the central atom, you will be looking at the electronegativity table, and the least electronegative element is going to be the central atom. In this example, we have only two atoms, hydrogen and oxygen. We know hydrogen can never be the central, so it is the oxygen that will be in the center. We don't have to look at the electronegativity table. We can draw hydrogens around this oxygen. Then we look at how many electrons are already in this structure. So each straight line have 2 electrons. So we have 2 electrons here and 2 here. 4 electrons are already there. We have to draw the rest of the dots. And remember, when we make the dot, we start from the terminal, we complete the octet, and then we go to the center. But for hydrogen, we never show any lone pair or any dot on the hydrogen. So based on the rule, we should start from the terminal, but since the terminal is hydrogen, we are not going to draw any dot here, and we will draw the rest of the 4 dots on the oxygen. So we have 4 dots to draw, and we have the rest of the 4 dots here. Next, we check the octet to make sure that the octet is complete and do it for hydrogen. So for hydrogen, we have 2 electrons here. For oxygen, we have 2 electron here, 4, 5, 6, and 7, 8. So the duet for oxygen is complete as well. Let's find the steric number for this oxygen. So for steric number, we count the lone pairs as one steric number, right? So we have one steric number here, 2 here, 3 here, and 4 here. So steric number for this is 4, right? Based on 4 steric number, the whisper arrangement is going to be tetrahedral, right? You can go back to the table, you can rewind the video, go back to the table, and you will see from that table that for 4 steric number, the whisper arrangement is tetrahedral. So here you are going to write down name tetrahedral. You can also write down the bond angle. So bond angle here going to be 109.5 degree. The three-dimensional drawing is the three-dimensional drawing of this whisper arrangement. This is what we learned how to draw for, okay, this is how we draw the tetrahedral. We have oxygen in the center, we have 2 hydrogens, and then we have lone pairs. This is the three-dimensional drawing. The shape is going to be, you are going to ignore these lone pairs, and when you ignore the lone pairs, the shape is going to be bent. Okay, the bond angle for the bent shape is going to be less than 109.5. Even here, since you know it is already lone pair, so you should say less than 109.5. Bond polarity molecular shape, we will wait for the next topic to come, and then we will come back here and complete the rest of the side. For ammonia, the Lewis dot structure, you have to pick the central atom, and again there is only nitrogen and hydrogen. Hydrogen can never be the central, so it is only nitrogen that will be in the center, and then you can draw the rest of the atoms around nitrogen. We have 6 electrons already here, 2 for each bond, so 2, 4, 6. We have to draw 2 more. We cannot draw on any of these hydrogens, so it will go only on the nitrogen. With this, you can see that the octet of nitrogen is complete and duet of hydrogen is complete. when you check the steric number, this lone pair is going to be 1, steric number 2, 3, and 4. So steric number for this is 4. Based on 4 steric number, the whisper arrangement is going to be tetrahedral. And since there is a lone pair, the bond angle is going to be less than 109.5. Okay. Again, the three-dimensional drawing will be for tetrahedral. It will always be this. You just have to arrange the, okay. The shape, when you are giving shape, you are going to ignore the lone pair from here, and this bottom part is bent or less than 109.5 degrees. Let's do next example. In this example, our central atom is carbon, and then we have 4 hydrogens around this carbon. If you count the number of electrons already in this structure, you will see that there are 8 electrons, 2, 4, 6, and 8. So all electrons that you have to show in this structure, they are already there. We have to count the steric number for this central carbon, and the steric number for this is 4. There are 4 electron groups, 1, 2, 3, and 4. With a 4 steric number, electron group arrangement is going to be tetrahedral, and bond angle will be 109.5. Remember, if there is a lone pair on the central atom, then the bond angle is less than 109.5 for the tetrahedral arrangement. But in methane, there isn't any lone pair, so the bond angle will be 109.5. 3D drawing will be for tetrahedral. We always draw it like that. You have to do this practice how to make the 3D of tetrahedral. Okay, and then you can just have all these hydrogens at the corners and carbon in the center. Okay, in this tetrahedral, all are the bonding electrons and there isn't any lone pair, so the electron group geometry and the shape will be same. So for this shape of the molecule will be tetrahedral. Okay, and bond angle again 109.5. In the next example, first of all, we have to make the connectivity. So connectivity is like this. Um, and after making connectivity, if you count number of electrons already in this structure, you will see we have 2, 4, 6, 8, and 10 electrons. And you have to make 2 more dots here, like there are 12 electrons that you have to show. So 2 more dots. We cannot make these dots on any of these terminal hydrogens. We have only these 2 carbons left, so we can make those 2 dots on any of these carbon. By making these 2 dots, you can see the octet for this carbon is complete, 2, 4, 6, and 8, but the octet for this carbon is not complete. So this carbon will get lone pair of electron from adjacent carbon, which is this. And when it get this, then there will be a double bond here, and with this double bond, octet for both carbons is complete. After this Lewis-Dot structure, next step is to count the electron group or steric number. So single bonds will be counted as 1 steric number. So 1 steric number here, 2 steric number here, and multiple bonds are also counted as 1 steric number. So this is the 3rd steric number for this carbon. So this carbon have 3 steric number, and if you count for the other carbon, so remember in this Lewis structure, there are 2 central atoms. Central atom is the atom that is connected with 2 or more atoms. So this carbon is connected with 3. So this is a central. Now if you count the steric number for this, you can see it has 1, 2, and 3. So this carbon also have 3 steric number. Based on 3 steric number, the electron group geometry around each carbon, since both carbons are identical, so we are doing it around each carbon based on a steric number. The electron group geometry is trigonal planar, and the bond angle will be 120 degree. Okay, now let's make the 3D drawing for this molecule. So we have one carbon which is trigonal planar, and this is our trigonal planar, right? But the second carbon as well is trigonal planar. So if we are making trigonal planar for that carbon, your shape is going to be like this. So both are, this carbon is trigonal planar and this carbon is trigonal planar. Now the shape of the molecule around each carbon, there isn't any lone pair, all are bonding electrons. So whatever the electron group geometry is will be the shape of the molecule. So around each carbon, shape of the molecule will be trigonal planar. Okay, let's do the next example. Again, first we are going to make the connectivity, and after making connectivity, you can see that there are 4 electrons already in this molecule. You have to make rest of the 6 dots to have total of 10 electrons. So we will start making from the terminals. We cannot make any electron lone pair of electron on hydrogen, so it is nitrogen where we are going to show those dots. So we have 1, 2, 3, 4, 5, 6. With these 6 electrons, octet for nitrogen is complete, but octet for carbon is not complete. So carbon will get lone pair of electron from adjacent nitrogen, and when it get those electrons, there will be actually 4 electrons that carbon need, and after that you will see that there is a triple bond here. Now the central atom for this molecule is only one, which is this carbon. And if you check the steric number for this carbon, this single bond is one steric number and this multiple bond is the second steric number. So steric number for carbon is 2. Based on steric number, electron group geometry around carbon is going to be linear, and bond angle will be 180 degree. Linear drawing will be, you will be just making them straight like this. Okay, and shape of the molecule will also be linear. Okay, let's do the last example. Here you have to first do the connectivity. After this connectivity, you are going to count the number of electrons that we have in this structure. So we have 2, 4, 6. Each straight line is 2 electrons. So we have 6 electrons already here. We have to make 4 more electrons, and I cannot make any of those electrons on hydrogen. I will start with the carbons. I can make all those 4 electrons on this carbon. Octet for this is complete, but octet for the other carbon is not complete. So this carbon will get electrons from adjacent carbon and actually need 4 electrons. There will be a triple bond. With this triple bond, if you check octet for this carbon, it is complete, and octet for this carbon is complete as well. 2, 4, 6, and 8 electrons. Next step, you are going to check steric number. So for this carbon, the steric number, single bond is one steric number, multiple bond is another steric number. So steric number for this carbon is 2, and steric number for the second carbon as well is 2. Around each carbon, geometry is going to be linear based on 2 steric number. Bond angle will be 180. If you're making the 3-dimensional drawing, it will be linear, and the shape around each carbon will be linear as well. Let's look at the types of covalent bonds. We have 2 types of covalent bonds, nonpolar covalent bond and polar covalent bond. If you look at the examples here, I have hydrogen molecule and hydrogen fluoride molecule. The biggest difference in these molecules, beside their elemental composition, is in their bonding. As a hydrogen bond or a hydrogen molecule have only one type of element, that element have same electronegativity. So due to the same electronegativity, the sharing of electrons is equal. Whereas in hydrogen fluoride, electronegativities of hydrogen and fluoride are different. This unequal electronegativity means that the bonding electrons will spend more times around the fluoride atom and less time around the hydrogen atom. This inequality produces a molecule with a partial negative charge on the more electronegative fluoride atom and a partial positive charge on the less electronegative hydrogen atom. If you're not sure about this, you need to review electronegativity's topic from the previous chapter. We can also find the polarity of a molecule with the help of this opposite charge plate test. So what we did in this test is we have two oppositely charged plates, negatively charged and positively charged, and we have hydrogen molecule and hydrogen fluoride molecule within these two plates. So if you look at the behavior of these molecules, you can see that the hydrogen is just randomly floating with between these plates and have no effect of these negative and positive charge. Whereas hydrogen fluoride, all the partial fluorides have arranged themselves towards the positive charge plate because the unlike charges attract each other, and all the hydrogens have arranged themselves towards the negatively charged plate, so that because the opposite charges are attracting each other. And based on this behavior, we can say that this hydrogen fluoride is polar molecule and hydrogen is a nonpolar. Let's see how to indicate the polarity of a bond. Polarity of a bond can be indicated with the help of an arrow that points from positive charge to the negative charge. The arrowhead points to the negative end of the bond, and arrow is crossed at the positive end like this. The arrow represents a property of the bond called dipole moment, which is the measure of the polarity of the bond. And longer arrow means larger dipole moment, and shorter arrow means less dipole moment. So if you look at the electronegativity difference between hydrogen and chloride and hydrogen and fluoride, you will see that this bond is more polar and this is less polar if you compare these two. And this is indicated by these dipole moments, that here we have a shorter dipole moment and here we have a longer dipole. Physicists refer these arrows as vectors. A vector can be best thought of as a number that have a direction. So these vectors or these arrows, they have a number associated with it, like more polar, less polar. There's a quantity, and also there's a direction. They always points towards the more electronegative element. In this slide, we will see how to add vectors. Vectors, when they are pointing in the same direction, will add. For instance, if we have a point A, a bus at point A, and then this bus travels to point B 2 miles, okay, and then from point B, the bus travels to point C 2 mile. These are vectors, right? They have a quantity and they have a direction. So these two vectors, if they are in same direction, we will simply add them, and if you want to see how far is A and C, you will be simply adding and you will get the number, which is 4 mile, and that's what we did here. Whenever we have vectors in the same direction, we simply add them. If the vectors are equal in quantity but opposite in direction, they simply cancel each other. Okay, this you can understand that you have a bus at point A goes to point B with 2 mile and then comes back to point A with 2 miles. So you can simply see that they just cancel each other. Okay, But if the vectors are in opposite direction, but the quantity is different, okay? So if you have, that's this scenario, that if they are opposite but the quantity is different, then there will be some net result, okay? Now, if the vectors are at angle with some each other, then the resultant vector will have the length that can have any value between 0 and the sum of the length of those original vectors. You don't really have to worry about what is the actual quantity of those vectors. You just need to know that when the vectors are at some angle, they will have a positive net value. Okay, so the only time they cancel each other is when they are equal in value and opposite in direction. All other cases, there will be some net number. Let's look at molecular dipole moment. In the previous slide, the dipole moment that we saw here is the bond dipole moment. And since in this molecule there is only one bond, so this bond dipole moment is happen to be the molecule dipole moment as well. But if there are many bonds in a molecule, then the molecular dipole moment can be different than the bond dipole moment. So, molecular dipole moment actually shows the net dipole moment for the entire molecule. It points from the partial positive end of the entire molecule to the partial negative end of the molecule. And remember that only polar molecules will have molecular dipole moment. Okay, so far what we have learned is that the dipole moments in same direction will add up and give a positive net or molecular dipole moment. And the molecule will be a polar molecule. The dipole moment in the opposite direction with same magnitude will cancel each other and will give you a zero net or molecular dipole moment, and the molecule will be a non-polar molecule. The dipole moments that are at some angle will give a positive net value or the molecular dipole moment, and the molecule will be nonpolar. So the molecular dipole moment shows the net dipole moment for the entire molecule, and it points from the partial positive end of the molecule. Like for instance, here you have the partial positive end for water molecule. So the molecular dipole moment will points from the partial positive end of the entire molecule to the partial negative end of the molecule. So in water, these individual dipoles that we have, right? We have one dipole here and one dipole here. These dipoles are at some angle, so they will give you some net positive value, and the molecule will be polar. So if the molecule is polar, you are going to show a molecular dipole moment, and that molecular dipole moment will be from partial positive end to the partial negative end, and there will be a cross like this. And you can see this in this image as well. Now, when we come here in dichloroacetylene, we have dipole moments for the bonds. We have for the bond between carbon and chloride, and we have here for between carbon and chloride. But if you look at the magnitude of these dipole moments, so they are the same bonds, right? So if the bond is same, whatever value you have, it will be the same value. So same value but the opposite direction, so they are going to cancel each other, and there will be the net dipole will be 0. So if the net dipole is 0, this molecule is going to be a non-polar molecule. So this is a slight difference that you need to know. We have a bond dipole moment, right? So the bond dipole moment depend on the electronegativity table. For instance, if I have to find whether this hydrogen and oxygen bond is polar or not, I will look at the electronegativity table. And if there is a difference in electronegativity, then this bond is going to be polar, and that's how we made this bond dipole moment. For the molecular dipole moment, you have to look at holistically on all the dipoles that we have in this molecule and see whether they are canceling or adding up to a positive number. And if they add up to a positive number, the molecule will be polar. But if they cancel each other, then the molecule will be nonpolar. Here we have some steps how to determine whether a molecule is polar or nonpolar. Step number 1 is you need to draw Lewis dot diagram. Step number 2 is you will be applying whisper theory to determine the shape of the molecule. Then you will draw three-dimensional shape of the molecule and you will show all bond dipole moments. This bond dipole moments you will be doing it with the help of electronegativity. If there is a difference, there will be a bond dipole. Then you will determine whether the individual bond dipoles are canceling or are they giving you a net dipole moment for the molecule. Okay, so if they give you a net dipole moment for the molecule, then the molecule will be polar. Let's do this example. Here we have to determine whether SiBr4 is a polar or non-polar molecule, and we have to indicate the direction of a polar direction of molecular dipole moment if one is present. You guys can pause this video, draw the Lewis dot diagram for this molecule at your own, apply whisper theory to determine the shape of the molecule, and draw a three-dimensional shape showing all the bond dipole moments with the help of electronegativity table, and determine whether the individual bonds dipole moments cancel or whether they give you a net dipole moment. So do all these steps at your own and then play the video to check your answer. The first step is to draw the Lewis dot diagram for this, and for Lewis dot diagram the first step is we need valence electron. For silicon we have 4 valence electron, for bromine we have 7 valence electron, and we have 4 BRs, so altogether 28 electrons. And when you add these, you will get 32 total electrons for SiBr4. You can have your Lewis dot. Silicon is going to be the central atom based on less electronegativity. You can refer to the electronegativity table. And then we have all 4 bromides around it. There are 8 electrons already in this structure, 2, 4, 6, and 8. And you have to make rest of the electrons to have all 32 electrons here. So after 8, I'm going to start making the dots. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All 32 dots are here, and with all these 32 dots, if you check the octet is complete for all these bromides and for silicon as well. So our Lewis dot diagram is complete. Next, we have to use whisper theory to determine the shape of the molecule. For that, we need a steric number around the central atom. So silicon is the central atom. Around silicon, we have 1, 2, 3, and 4. For 4 steric number, electron group geometry is tetrahedral. So I'm going to draw tetrahedral here. We have 4 bromides at the corner, and we have silicon in the center. And the bond angle here going to be 109.5 degree. And the name for the electron group geometry is tetrahedral. For shape of the molecule, since there isn't any lone pair, so electron group geometry is also the shape of the molecule. Next is you have to show all bond dipole moments. So for this, let's write down the electronegativity. So silicon's electronegativity is 1.8, and bromide's electronegativity is 2.8. And the bond dipole moments go from the partial positive to the partial negative. So silicon will be partial positive as its electronegativity is less. So our bond dipoles are going towards the bromide. We have 4 bond dipoles. So here we have all 4 bond dipole moments. Next step, you have to see whether they are adding up or canceling out. So adding up all individual dipole moments can be tricky for the molecules with more than 3 atoms. However, there is a quick way to determine whether or not they cancel is by doing a tug of war test. To perform this test, imagine that these are tugs pulling this silicon towards themselves with the same strength. So if they all four sides are pulling the silicon towards themselves with the same strength, you have to ask a question whether this silicon will move. And if your answer is no, then it means that this molecule is non-polar. And in this case, if I ask this question to myself that we have four bromines pulling this silicon towards themselves with the same strength, will this silicon move? My answer is no, silicon will not move. And if the silicon will not move, this molecule will be a non-polar molecule. And for non-polar molecule, we don't have any net dipole moment, so I'm not going to draw any net dipole moment here. Let's do another example. In this example, you have to determine whether ammonia is a polar or non-polar molecule, and you have to indicate the direction of molecular dipole moment if one is present. Again, pause this video, do all these 4 steps at your own, and then come back and check your answer. So first step is to draw the Lewis dot diagram. For ammonia, we have 5 electrons here. For hydrogen, we have 3 electrons for all 3 hydrogens, and altogether there are 8 electrons. Nitrogen is going to be the central atom. With this connectivity, we have 6 electrons already in this structure, 2, 4, and 6. We have to make 2 dots, and those dots will go on the nitrogen as we cannot make any dot on the hydrogen. With this, if you check, the duet for all hydrogens is complete and octet for nitrogen is complete. So this is my complete Lewis dot structure. To find the whisper geometry, we have to count steric number. And for a steric number, we count lone pairs as one steric number, and we count single bonds as one steric number, right? So altogether, you can see we have 4 steric number, and for 4 steric number, electron group geometry is tetrahedral. The electron group geometry is tetrahedral. Bond angle, since there is a lone pair, there will be a squeeze play. This is more negative, will push these bonds closer, and the bond angle is going to be less than 109.5. Now, the shape of the molecule, when you are giving shape of the molecule, you are going to ignore this part, right, the bottom one. And with this, the shape of the molecule is going to be pyramid. Now, if I have to make the dipole moments, we know that nitrogen is more electronegative and hydrogen is less electronegative. So the bond dipole moments will be from hydrogen to nitrogen. And these dipole moments that we have, they are at some angle. Remember, there is a hydrogen, there is a lone pair here that we are not looking at right now. So all these dipoles are at some angle, and whenever the dipoles are at some angle, they will give you a net dipole. And the net dipole, when you draw, it will be from the positive end of the molecule, which is all these hydrogens are positive and the nitrogen is negative. So the net dipole that you are making will be from the positive end to the negative end, and it is going to be like this. Okay, so this molecule will be a polar molecule. Now let's complete the rest of the columns in this worksheet. So to find the bond polarity, whether the bond is polar or non-polar, you need electronegativities. So electronegativity for oxygen is 3.5 and hydrogen is 2.1. So you can see that there is an electronegativity difference, and whenever there is a difference, the bond is going to be polar bond. For the molecular polarity, you have to see whether these dipoles are canceling or if they are in some angle. So you can see here we have the dipoles in some angle. So they are not canceling, but they will add up. So the net dipole moment will be from the positive end to the negative end, and this molecule is going to be a polar molecule. For resonance, resonance is present in the molecules where there is more than one possibility of making a double or triple bond. You don't see that in the water molecule, so the resonance for this will be no. The next example that we have is for ammonia. Electronegativity for nitrogen is 3.0, for hydrogen it is 2.1. So there is electronegativity difference. So the bond is going to be polar. For the molecular polarity, you are going to look at these dipoles, whether these dipoles are getting cancelled each other or not, and you can see that these dipoles are not cancelling, they are at some angle. So whenever they are at some angle, they are not going to cancel, but they will add up and give you a net dipole, and that net, due to that net dipole, the molecule will be polar. There isn't any resonance in this molecule because there isn't any double or triple bond. So answer for this going to be no. Then here we have a methane molecule. Electronegativity for carbon is 2.4, for hydrogen is 2.1. There is a very slight electronegativity difference, but based on our definition, the bond is polar. But if you look at the electronegativities and the dipoles will cancel each other, because if you do the tug of war test, you will see that all these dipoles will simply cancel each other. Okay, and when they cancel each other, the molecule will be a non-polar molecule. And for resonance, there isn't any double or triple bond, so no possibility of having a resonance in this. For this molecule, we have 2.4 electronegativity here, 2.4 electronegativity here, and 2.1 electronegativity here. So the bond between carbon and carbon is going to be a non-polar bond, but the bond between carbon and hydrogen will be a polar bond. Now here I want you to remember one thing, that molecules between carbon and hydrogen are always non-polar. So you don't even need to do a tug of war test, okay? So whenever you see a molecule between carbon and hydrogen only, it will be a non-polar molecule, because eventually, so first of all, the bonds are very slightly polar, right? Just zero point 0.3 is the difference. And then all these dipoles that we have, they are going to eventually cancel each other, and the molecule will be non-polar molecule. Okay. Now for resonance, there is a double bond here, but this double bond is a fixed double bond. It in resonance, the double bond, there's a multiple possibilities of having a double bond. Sometimes we have a double bond here, and the next instance, it is possible that the bond open up and it make a bond some other place. But we don't see that here, so there is no possibility for resonance in this molecule. Next, we have hydrogen, carbon, and nitrogen. So hydrogen is 2.1, carbon is 2.4, nitrogen is 3.5 electronegativity. So yes, carbon-hydrogen bond is polar, carbon-nitrogen bond is polar. For the molecule, if you look at the dipoles, so the dipole goes from the less electronegative to more electronegative. So the dipoles are going in the same direction, right? So they're going to add up, and this molecule will be a polar molecule. And again, this multiple bond that we have here, this is a fixed bond. So the resonance for this is going to be no. In this next example, our carbon-hydrogen bond is polar, carbon bond is non-polar. The molecule is between carbon and hydrogen only, so this is going to be a non-polar molecule. And for resonance, this multiple bond that we have here, this is a fixed bond, so this is going to be no resonance possible. For resonance, if you want to see the example where resonance is possible and you want to clarify some things, compare these examples with carbon dioxide Lewis structure. You will see that in carbon dioxide there are more than one possibilities of making a double bond, and that more than one possibilities are actually called the resonance.